So for the rest of today's session, I'll be doing Charliecloud, putting the U in GPU. This is based off of some GPU-specific Charliecloud training I developed in the last year. And I will do a kind of an interactive demo. But if you have any questions or want to go into things deeper, please stop me. Kind of just have a rough plan and you go to whatever you go through. So I'll start with some slides, kind of go back and forth, and just really hope this really big GPU container pulls. So yeah, so kind of just high level kind of slides and things we'll go through. We'll do a little introduction and into technical differences between running a CPU container and GPU. Then we'll go into best practices and common gotchas I've seen. And then I'll have a demo kind of scattered throughout. But interrupt me if you want to go off the path. So introduction. So why NVIDIA GPU containers? The short answer is AI. But you get the performance, you get the benefits of a container workflow with the performance advantages of GPUs. But there's lots of extra, or not lots, there's a couple of extra considerations that are needed for your GPU containers. The big one is you need access to the GPU driver, which has been the biggest pain point for me in the last month. Also, architecture-aware containers have become a very high gotcha with GPU containers. Also requires NVIDIA Container Toolkit, which is an admin issue. I guess technically that's not true anymore because it's NVIDIA Container Toolkit or NVIDIA SDK. So technical differences. Cool. Let's do this demo. Let's see if it pulled. I'll wait for that to keep put like. Sorry, kind of jumping around. So the biggest kind of difference and thing to think about is how do we get libcuda.so in the container? It's relatively straightforward with Charliecloud, but it's an annoying thing to think about. So over here we have our container image that has our application and the CUDA toolkit. Then over here we have our host on our GPU node that has the NVIDIA display driver package, along with libcuda.so and NVIDIA.ko. And kind of the way we get access to libcuda in the container is we expand the container to kind of just include libcuda.so. Now they can communicate and it works and it's grand. Let's see if that finished pulling. It's so close. Okay. Sorry, let's go back. Go on. What is happening with this Docker? Sorry, I'm currently also on VPN, so I'm like double issuing here. Turd. Okay. There. So this is the Docker file I'll be working with and going through. So we're pulling an NVIDIA CUDA image, which takes a bit. It's also doing update and apt-get install, as well as installing Python, or it's installing Python and Python pip. Then afterwards, it's pip installing NumPy and Torch, which is what currently the build's stuck on. So currently, this is the step I'm running, chimage build, and I'm calling it GPU. So I was able to pull the image straight from Docker Hub, and I pulled it straight onto the GPU node because architecture-aware containers is the vein of catches me every single time. And the only way I can get across it is just pulling straight from the node. So this is currently building. Yeah. So what we'll kind of go through next is how it works to run, or why do we need to do the NVIDIA host injections and how to do so. And hopefully this is done. Oh my God. Do you know what? I think I have it pre-built. Sorry, we're just gonna switch to use my pre-built one. Sorry, since the container is so big, I'll make that text bigger. Yeah, so currently what's happening is the container takes a while to build. I pre-built it. I stored it as a squash.fs just so it's more compressed and I don't accidentally break it just from not understanding file systems. So currently I'm converting it from a squash.fs into a directory format, so I'm able to play around with it, show how things break. So that's a lot quicker than installing NumPy in a container using conference Wi-Fi and lab VPN. Sweet. So I pre-pulled the container just to kind of show I'll hop into that directory. So this is inside the container. It's a container, nothing too special. And then this is just to show what GPU node I'm on. Yeah, so I'm currently on an NVIDIA GPU node, which was very stressful because all of our open systems are currently down at the moment for upgrades. So everyone is running on this one, so I had a little scary moment, almost not being able to get a GPU. But just, let's see. Cool. So we are gonna run this example right here. So I don't do live demos, okay. Oh, sorry. Stupid hyphens or dashes. Okay. Cool. This is what I wanted. I wanted to fail. Now I'll explain what's happening now that I copied things over correctly. So it might be a bit hard to read, but I'm just doing so. This is the container. Haven't done anything with it. It's built with CUDA installed, NumPy, and all that fun stuff. So I did chrun to run the container, and then inside the container, we're running this right here, which is pretty straightforward. It's just Python, and we're importing Torch and trying to run torch.cuda.getDevice. But then we got this error message, which kills me. So anytime you see a runtime error, no found NVIDIA driver on your system, that means you forgot to do your NVIDIA host injections. So in Charliecloud, there's two different ways to do that. So the kind of old way is to use ch from host, which manually does it. Cool. So this is the old way, so I ran ch from host -- NVIDIA because I told the command you want to import all the NVIDIA OCI hooks. And what's interesting about this format, or not interesting, but what makes this kind of command slightly inconvenient is that it absolutely has to be in a directory format. So in the second way, or newer way I'll show you, you'll be able to do it in a squash.fs format. So it just makes it a bit cleaner. So what this ch from host does, it binds mounts everything that comes from Let's see, NVIDIA. Is this the right one, Reed? Nope, it's not. What's the command that CHRMOS does? Okay. Well, there's an NVIDIA command that runs it. I don't. Sorry, backtrack. Just did the NVIDIA host injections in the directory format. So it stayed, it's good. So now when we rerun that chrun command, it works. So it works, it's happy now that it has access to the NVIDIA host. So now Charliecloud has a way cooler way of doing it, which is with CDI container device interface. I think I have slides on that. So CDI, it's cool, container device interface. So kind of the main use case is that, as I said before, you need libcuda.so inside your container for your GPU workflow. But libcuda.so can't be containerized, and anything along with that, anything inside the kernel can't be containerized. So I'm going to run this command, but since this text is bigger, I'll show it here first. So in order to use CDI, all we have to do is include a -d flag in the chrun command. Makes it a bit easier is that it can be in a squashfs format. There is, from an admin perspective, there is 2 extra steps to get that working. One of them is creating a cdi.json file, and there's an extra libjson.so that needs to be installed. I'll explain more of that tomorrow when I talk about how I do the modules on a testbed cluster. But this one extra command, or one extra argument in chrun, not an extra command, can stay in a squashfs. So let's backtrack here. Sweet. So it worked. One command. Yay. So it's more just switching to using the -d and CDI. Just makes things a bit cleaner and easier for the users. It's also now kind of an industry standard to use CDI. Yeah. Cool. Sweet. Oh, can I copy and paste this? Okay, so this is kind of the second. Are there any questions? I'm kind of just going through things. What does it stand for, Reed? Use. Device, okay. -d stands for device. It should be -cdi.
I mean, you can. It's -cdi if you want.
I should really read the documentation. I didn't know that. Cool. Yeah. So this command just runs the same GPU container, but this time it shows that it has access to every CUDA device. Now I get. Oh, this is horrible doing this live. Okay. Sorry for bearing with me. I give up. Okay, well I give up, but this is the output it's going to show. But in this case, it would still be 4, but I would say NVIDIA Git Force. Cool. Yeah, so and this works with doing a directory format with ch from host, as well as just doing the NVIDIA CDI import. That was kind of horrible. 3 questions about that. I will say we have documentation on this on the Charliecloud docs, and it's something that's I'm actively updating because it's constantly changing and I want to make it better. But if you do start running your GPU workflows and you notice something Charliecloud doesn't have, or if you think something's not optimal enough, please let us know. We like to fix things, or I like to tell the developers to fix things. And the more users we have with eyes on it, the faster we're able to get things working, because we want things to work for you. Okay. Best practices. This next chunk is very much constantly updated. Every time I have a user ticket with a new gotcha that I wasn't expecting, added to this slide for future reference. This one I definitely emphasize more than the rest because it's the one I run into the most, mainly because at Lano we have 2 GPU nodes in production and they have different architectures. So a lot of users try to run our open GPU cluster that expect to run that same exact container on the one on the classified network, but they're different architectures. So I always overly emphasize this point. So for example, this is an example with running an open MPI container that was built on Lano's Venado system. But we're doing it on Tacoma, and there's different architectures. And you get this fun error message. Did that get fixed to be more descriptive, or is that still an issue?
It's either fixed or coming soon.
Okay. This error message is not very descriptive, so it's fixed, or maybe soon, hopefully. The fix is pretty straightforward since you're already able to successfully build it once. And usually you can just keep the same Docker file and run it on that system and just rebuild it however long it takes. And that's currently the best solution that takes the least amount of kind of effort on the user's end. So what I actually started doing is I started labeling all my containers for which architecture, which system I built them on, because I build a lot of test containers and I forget what architecture I built it for. And then I have to rebuild containers 18 million times. And I don't have the patience to pull NVIDIA containers that often, so I just get frustrated and yell at my screen. Yes, large data movement. So this is more so with kind of AI versus GPU containers. So my suggestion is doing bi-mounting your data versus storing your data directly inside the container. So in order to access your data outside of the container, you just have to specify what paths you want to include with -b, and that way you're able to update your data without having to rebuild your container. This one, someone said I had to add because they accidentally got burned with -W or -- write fake. That is the option that allows you to edit a container interactively. But all the changes are discarded after exiting the container. So don't use -- write fake unless you are 100% sure you do not want any changes saved. Cool. Yeah, so with NVIDIA's large containers, storing, sharing, kind of moving large containers is kind of a pain in the butt. But these are kind of some things that me and the AI folks have come to make it as least painful as possible with the hopes of making it better. Continue making this process better in the future. So first, just to save a bit of time using transfer or any data movement tools, I'd suggest to convert it to Squash Fast. That just makes it more compressed. Also read-only, so it doesn't accidentally, no one accidentally edits it. That's Lano specific, but if you have any file transfer nodes at your institution, use those. I've seen better performance on those. They're running direct on compute nodes. I think also just be aware of your storage type. So what storage is persistent storage and what is there. And what's temporary storage? And just be aware of your specific institution's file system rules. So yes, there's this persistent storage, but usually it has smaller quotas. On the other hand, you have temporary storage, but usually there's some gotchas with some purge policies. That's all I had. I was kind of hoping that was going to take a while. I don't know if there's any questions. I was hoping like be more interactive. Definitely kept it open-ended on purpose. So anything folks want to say or complaints or things they want added with Charliecloud, I'm all ears. This is obviously still a work in progress.
So you showed the NVIDIA workflow. Is there something similar for ROCm-based systems like Alcap?
Do we have anything? Read.
We haven't. Does the ROCm stuff also need the stuff injected? Maybe. Maybe. Yeah, I don't know.
Yeah. No one's asked about it yet, but I'll test it. I have access to Alcap.
But probably they're also going to have a driver and maybe some things that is system specific. So.
Yeah. Yeah, I'll take a look once I'm back on site next week. I shouldn't be that much of a lift, but I don't want to stick my foot in my mouth.
Jordan makes containers for LAP. If he has a container from RZ Adams, he might have done some stuff for ROCm.
Oh, cool. So I'll test that out. Yeah. Any other questions or comments?
What was the impetus for using SquashFS? I guess it's not a question for you, but I guess.
Yeah. Yeah. So I'll like to say I'm very biased towards the SquashFS workflow because that's the workflow I developed when I was an undergrad student. But I think the main reason for it, especially now with the AI and NVIDIA containers, it's compressed, smaller, less storage. It's read-only, so currently I suggest SquashFS containers a lot for projects and code teams trying to share their code with containers because they're able to just save one container at their project space in a shared location, and then all their users are able to use the exact same container. Unless they actually like physically delete the whole file, they are not able to modify it or corrupt it because it gets mounted in a separate location. And it just makes things a little bit tighter because there's more room for error and corruption using a directory format. So it just smooths out the process. Less room for user error.
The parallel file systems are not good at metadata. So another reason is if you use a SquashFS, then all the metadata becomes data effective with the cluster. So that performance improvement.
Yeah.
More of a comment, but there's an equivalent AMD CTK that generates a CDI spec for ROCm.
Oh.
Ooh. Thanks, Elena. Anything else? I was just call it really early and just give people their afternoon back. Cool. Sorry that was rough. Bother me if you have questions about this. Can talk about it more in detail, depending on specific questions. But yeah, see you all tomorrow for more Charliecloud talks. Hopefully it didn't scare you away. We'll have more variety of speakers tomorrow and more technical things.